Error detection and correction. Networks must be able to transfer data from one device to another with acceptable accuracy. There are many factors that can alter one or more bits of a digital message. Some applications require a mechanism for detecting and correcting these errors. Data can be corrupted during transmission. Some applications require that errors be detected and corrected. Types of errors. The term single-bit error means that only one bit of a given data unit, such as a byte, character, or packet, is changed from 1 to 0 or from 0 to 1. In a single-bit error, only one bit in the data unit has changed. If you look at the example below, you can see that one of the bits from the sent message was changed. This might be due to noise in the transmission line, or maybe even noise in the receiver itself. Anyway, what changed is the middle of the message from a bit 0 to a bit 1. The term bust error means that two or more bits in the data unit have changed from 1 to 0 or from 0 to 1. A burst error means that two or more bits in the data unit have changed. Please see the image below. As you can see, there are 4 bits that were corrupted. So they all changed from 0 to 1. Redundancy. The central concept in detecting or correcting errors is redundancy. To be able to detect or correct errors, we need to send some extra bits with our data. These redundant bits are added by the sender and removed by the receiver. Their presence allows the receiver to detect or correct corrupted bits. Detection versus correction. In error detection, we are looking only to see if any error has occurred. The answer is a simple yes or no. We are not even interested in the number of errors. A single bit error is just the same for us as a burst error. In error correction, on the other hand, we need to know the exact number of bits that are corrupted, and more importantly, their location in the message. The number of errors and the size of the message are important factors. Error detection. Error detection is the process of monitoring data transmission and determining when errors have occurred. These techniques neither correct errors nor identify which bits are in error. They only indicate when an error has occurred. Its purpose is not to prevent errors from occurring, but to prevent undetected errors from occurring. The most common type of error detection is, of course, redundancy checking. Coding. Redundancy is achieved through various coding schemes. The sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. The receiver checks the relationship between the two sets of bits to detect or correct the errors. The ratio of redundant bits to the data bits and the robustness of the process are important factors in any coding scheme. Let's take a look at a basic block diagram for this. On the sender side, we have the encoder, and on the receiver side, of course, we have the decoder. For the encoder, we have first the message, which is the message that we want to transmit. It will then pass through a generator that will produce redundancy bits, depending on the message signal. The message, together with the redundancy bit, will be sent through the channel. Now, no channel is perfect, although some are better than others. But even in the best channels, an error may still occur. Once the message and redundancy gets to the receiver, the information will pass through a checker. Basically, what the checker does is it compares the message and the redundancy bits. If the redundancy bits are the correct bits for a certain message, then the checker will deem the received information to be correct and it will pass the receiver towards its destination. If the redundancy bits and the message bits do not match, then the message will be disregarded or discarded. Now, take in mind that this kind, it compares the message and the redundancy bits. If the redundancy bits are the correct bits for a certain message, then the checker will deem the received information to be correct and it will pass the receiver towards its destination. If the redundancy bits and the message bits do not match, then the message will be disregarded or discarded. Modular arithmetic. In modular arithmetic, we use only a limited range of integers. We define an upper limit called a modulus n. We then use only integers from 0 to n minus 1 inclusive, which means we can use the integer 0 and also whatever value n minus 1 is. This is known as modulo n arithmetic. Modulo 2 arithmetic. In this arithmetic, the modulus n is 2. We can only use 0 and 1. The following shows how we can add or subtract 2 bits. For adding, we can see 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1. And this is the last. The last one does not follow a base 10 decimal system arithmetic. It goes 1 plus 1 equals 0. To easily remember this, notice that modulo 2 does not use the integer 2. So when the answer becomes 2, it must go back to 0. Next, the subtracting. Subtracting basically has the same results as adding. 0 minus 0 equals 0, 0 minus 1 equals 1, 1 minus 0 equals 1, and 1 minus 1 is 0. Notice particularly that addition and subtraction give the same results. In this arithmetic, we use the XOR or exclusive OR operation for both addition and subtraction. The result of an XOR operation is 0 if 2 bits are the same. The result is 1 if 2 bits are different. Below are examples of bits that are under the XOR operation. So we can use the XOR operation on just 2 bits, or we can use XOR on 2 patterns of bits. Block coding. In block coding, we divide our message into blocks, each of k bits, called data words. We then add r redundant bits to each block to make the length n equals k plus r. The resulting n-bit blocks are called code words. Do not be confused with this. N is the total length of bits. It includes both k and r. K is the data word, and r are the redundant bits. With k bits, we can create a combination of 2 raised to k data words. With n bits, we can create a combination of 2 raised to n code words. Since n is always greater than k, the number of possible code words is larger than the number of possible data words. The block coding process is 1-to-1. The same data word is always encoded as the same code word. This means that we have 2 raised to n minus 2 raised to k code words that are not used. We call these code words invalid or illegal. How can errors be detected by using coding? If the following 2 conditions are met, the receiver can detect a change in the original code word. First, the receiver has or can find a list of valid code words. Second, the original code word has changed to an invalid one. Now this is just the same block diagram as before, but we have added k bits for the data word, this is our message. And after it passes through a generator, we have n bits. This is the code word. Code word is where we have added the r number of bits, which are the redundancy bits. And then onto the receiver side, we have again the n bits for the code word. It will pass through a checker. After passing through a checker, when the data word and the redundancy bits match, it will extract only the data words, which is composed of k bits. If the data word and the redundancy bits do not match, then the message will be discarded. That is how the receiver knows that the error has occurred. Error detection in block coding. The sender creates code words out of data words by using a generator that applies the rules and procedures of encoding. Each code word sent to the receiver may change during the transmission. If the received code word is the same as one of the valid code words, the word is accepted. The corresponding data word is extracted for use. If the received code word is not valid, it is discarded. However, if the code word is corrupted during a transmission, but the received word still matches a valid code word, the error remains undetected. This type of coding can detect only single errors. Two or more errors may remain undetected. Let us look at an example. Let us assume that k equals 2. So there are only 2 bits of data words and n equals 3. Therefore, r is equal to 1. We only have 1 redundancy bit. The table shows the list of data words and code words. Assume the sender encodes the data word 01 as 011 and sends it to the receiver. When the receiver receives the message 011, it will deem it to be correct. But if the first bit, the left bit, 0, was transformed into 1 through the channel, might be because of noise, and the receiver receives the code word 111, it is not present in the original possible code words. So it will be deemed a wrong message and will be discarded. But what if the receiver receives a message wherein the original message is supposed to be 011, but 2 of the bits got changed, so it goes 1, 0, 1. So 0 transformed into 1 and 1 transformed into 0. The receiver will receive 101. It will actually judge it to be correct, even though the original message was 011. So as you can see, with one error, the receiver can detect the error, but with 2 errors, the receiver can no longer detect the error. Another example, from the previous example, add 3 redundant bits to the 2-bit data word to make it a 5-bit code word. The table shows the possible data words and possible code words corresponding to each data words. Assume the data word is 01. The sender consults the table to create the code word 01011. And then the code word is corrupted during transmission and 01001 is received. In this case, the error occurred in one of the redundant bits. So the receiver checks 01001 if it matches any of the possible code words, which it will see that it doesn't match any, so it will disregard it and judge it as an error message.
But in case that both the data words were changed during the transmission, let's use the example 01011. So when both of the bits of the data word changed, so it goes 10011. The receiver would receive this message and it will check if it matches any of the code words. As you can see, it doesn't match any of the code word, so it will also judge this to be an error message. So in this scheme, in this coding scheme, we can see that multiple redundant bits will actually help in identifying more than one error. But one huge drawback for this is the redundant bits would also consume bit space or bit speed. So the system would actually have a lower bit speed than with less redundant bits. Hamming distance. The Hamming distance between two words of the same size is the number of differences between the corresponding bits. Hamming distance between two words, x and y, will be written as d, open parenthesis, x, comma, y, close parenthesis. The Hamming distance can easily be found if we apply the XOR operation on the two words and count the number of ones in the result. Note that the Hamming distance is always a value greater than 0 for two different words. Now this is an example of how to calculate the Hamming distance. Find the distance between the vectors 0, 1, 1, 0, 1, 0, 1, 0, and 1, 1, 0, 1, 1, 0, 1, 1. So to do this, we just apply the XOR operation. For the XOR operation, the result is 1 if the two bits are dissimilar, and if the two bits are similar, the result is 0. So as you can see, applying XOR would produce the result 1011, 0001. Now, they differ in 4 places, so the Hamming distance, the notation is D, then the first word, comma, the second word, that is enclosed in the parentheses. So the Hamming distance is 4, because there are 4 ones, meaning there are 4 places in which the bits are different for the two words. Minimum Hamming distance. In a given set of words, the minimum Hamming distance is the smallest Hamming distance between all possible pairs. Dsubmin define the minimum Hamming distance in a coding scheme. To find this value, find the Hamming distances between all words and select the smallest one. 3 parameters to consider. Any coding scheme needs to have at least 3 parameters. First, we have the code word size, n. Next is the data word size, k. And lastly, we have the minimum Hamming distance, dsubmin. A coding scheme C is written as C, open parenthesis, n, comma, k, close parenthesis, with a separate expression for dsubmin. Hamming distance and error. When a code word is corrupted during transmission, the Hamming distance between the sent and received code words is the number of bits affected by the error. The Hamming distance between the received code word and the sent code word is the number of bits that are corrupted during transmission. For example, if the code word 00000 is sent and 01101 is received, 3 bits are in error. And the Hamming distance between the two is this notation equals 3. Minimum distance for error detection. If S errors occur during transmission, the Hamming distance between the sent code words and received code word is S. If our code is to detect up to S errors, the minimum distance between the valid codes must be S plus 1, so that the received code word does not match any valid code word. If the minimum distance between all valid code words is S plus 1, the received code word cannot be erroneously mistaken for another code word. The distances are not enough, S plus 1, for the receiver to accept it as valid. The error will be detected. Error correction is more complex than error detection. This is because a decision is involved. When a received code word is not a valid code word, the receiver needs to decide which valid code word was actually sent. The decision is based on the concept of territory, an exclusive area surrounding the code word. Each valid code word has its own territory. Linear block codes. A linear block code is a code in which the exclusive or addition modulo 2, of two valid code words create another valid code word. Minimum distance for linear block codes. It is simple to find the minimum Hamming distance for a linear block. The minimum Hamming distance is the number of ones in the non-zero valid code word with the smallest number of ones. Parity check code. In this code, a k-bit data word is changed to an n-bit code word, where n equals k plus 1. The extra bit, called the parity bit, is selected to make the total number of ones in the code word even. Although some implementations specify an odd number of ones, we discuss the even case. By the way, if the parity bit will force the total number of ones in the code word to be even, this is called even parity. Likewise, if the implementation will force the number of ones to be odd, this is called odd parity. The minimum Hamming distance for this category is d sub min equals 2, which means that the code is a single bit error detecting code. It cannot correct any error. Let's take a look at an example for a parity check code. The code in the table is a parity check code with k equals 4, so there are 4 bits in the data word. With the addition of 1 parity check code, the bits in the code word becomes 5. Below shows a possible structure of an encoder at the sender and a decoder at the receiver. So as you can see, this is called even parity. Which means that the parity bit added for each data word is 1 if there are odd number of ones in the data words, and it will be 0 if there are even number of ones in the data word. So let's take a look at the second example for the data word 0001. As you can see, there are odd number of 1 in this data word. So a parity bit of 1 will be added to force the total number of ones even. So this is called even parity. The encoder uses a generator that takes a copy of a 4-bit data word. The 4 bits will have the labels A sub 0, A sub 1, A sub 2, and A sub 3, depending on which position the bits are placed in, and generates a parity bit R sub 0. The data word bits and the parity bit create the 5-bit code word. This is where n came from, n equals 5. The parity bit that is added makes the number of ones in the code word even. This is a simple block diagram for parity check code. Over at the sender side, we have 4-bit data words, a sub 3, the leftmost side, and a sub 0, the rightmost side. So the data words will be sampled by a generator which would produce a parity bit, R sub 0. After the transmission, the code word will be received by the receiver, and again, a checker will sample the message with the parity bit and judge if this code word is correct. If it is correct, it will send the data word to the next circuit. If it is incorrect, it will be discarded. Example. Assume that the sender sends the data word 1011. The code word created from this data word is 10111, which is sent to the receiver. So as you can see, this is still even parity. In this scenario, 5 cases may occur. First, no error occurs. This is the best case scenario, of course. Next, one single bit error changes A1. If the second case happens, so the code word now becomes 10011. As you can see, R sub 0 should not be 1 if that is the case, because this is even parity. So the checker would detect this error. It will know that one of the bits has an error and it will discard the message. Next, one single bit error changes R sub 0. When R sub 0 is changed, the code word now becomes 10110. And again, this is even parity. The checker will notice that this is an error code word, so it will again discard the message. For the fourth case, an error changes R sub 0 and a second error changes A sub 3. Now, let's look at the code word when this happens. Code word will now become 00110. As you can see, there are still even number of ones, and this is an even parity. So this error will go undetected because the checker will still judge this to be a correct data word. Lastly, 3 bits, A sub 3, A sub 2, and A sub 1 are changed by errors. So let's take a look at what will happen to the code word when this is the case. A sub 3 will become 0, A sub 2 will become 1, A sub 1 will become 0, and then the last 2 bits is still 1, 1. So it goes 0, 1, 0, 1, 1. As you can see, there are now odd number of ones. So this will be detected by the checker, and it will judge this code word as an error message. So as you can see, out of the 5 cases, the only unsuccessful check was due to the 4th case, wherein 2 bits were changed. So this isn't exactly a foolproof system. Next, this is a 2-dimensional parity check code. As you can see, there are row parities and column parities. This is for sending not just single characters, but a group of characters. So if you look closely, these are still even parities. So for the row parities, we will take a look at each of the data word and generate a parity bit for each data word. And for the column parities, we will take a look at the column for each of the data word. For example, in here we have 4 data words, and then to generate the column parities, we will take a look at the first bit of each data word and generate a parity bit for that column. Now let's take a look at what will happen if there is an error for the two-dimensional parity check code. When there is only one error, it can be detected and it can actually be corrected. As you can see, if only one error occurs, then it will affect two parities. So we can detect what bit the error occurred in. When two errors occur in a single data word, two parities will be affected, but only in the column parity. When three errors occur, four parities will be affected. And lastly, if four errors occur, this is actually unlikely, but it can happen. When four errors occur, this kind of parity check code can no longer detect the error. So the checker will still judge this as a correct message, even though there were errors. Hamming code. These codes were originally designed with dsubmin equals 3, which means that they can detect up to two errors or correct one single error. Although there are some Hamming codes that can correct more than one error, our discussion focuses on the single bit error correcting code. The relationship between m and n in these codes is n is equal to 2 raised to m minus 1. Types of redundancy checking. First, we have the checksum. Next, we have the vertical redundancy check, or VRC. Third, we have the longitudinal redundancy check, or LRC. These are usually used in conjunction with each other, the vertical and the longitudinal. Lastly, we have the cyclic redundancy check, or CRC. Checksum. Another relatively simple form of redundancy error checking, where each character has a numerical value assigned to it. The characters within a message are combined together to produce an error checking character. This is the checksum, which can be as simple as the arithmetic sum of numerical values of all the characters in the message. Vertical redundancy checking, or VRC. This is the simplest error detection scheme and is generally referred to as a character parity or simply parity. Each character has its own error detection bit called parity bit. This is what we have seen earlier. A single parity bit is added to each character to force the total number of logic 1s in the character, including the parity bit, to either be an odd number, this is the add parity, or even parity. Other forms of parity include marking parity, the parity bit is always 1, no parity, the parity bit is not sent or checked, and ignored parity, wherein the parity bit is always a 0 if it is ignored. Longitudinal redundancy checking, or LRC. This uses parity to determine if a transmission error has occurred within a message and is therefore sometimes called message parity. Each bit position has a parity bit, and this detects between 95% and 98% of all transmission errors. However, it will not detect transmission errors when an even number of characters has an error in the same bit position. Please look at this example. Excuse the handwriting. So we have the message radio. For each character in this word, there is an equivalent ASCII code. So for R, A, D, I, and O, the ASCII code is written above it. If you're curious as to how the ASCII code corresponds to each Roman character, please look at the right side of the image. You don't actually have to memorize this, but you do have to memorize that A is equal to the ASCII 41. Because after A, it goes B is equal to 42, C is equal to 43, D is equal to 44, and E is equal to 45, and so on, up until the Roman character Z. So for radio, it is 52, 41, 44, 49, and for F. And then let's write the ASCII equivalent into binary codes. So for 52, it's 0100101. It has a total of 7 bits from B sub 0 up until B sub 6. The digits from B sub 0 to B sub 3 is the first digit of the ASCII, and the digits B4 until B6 is the second digit of the ASCII. Now, as you have seen in the example before, we will apply LRC and VRC in this. We're just going to add parity bits. In this case, it is an odd parity. So as you can see, VRC is at the bottom. We've actually labeled this B sub 7. So we will force an odd number of ones. For R, there are 3 number of ones, so our parity bit is 0. For A, there are 2 number of ones, so it is an even number. We will add A1 for the parity bit to make it odd. And then D, there are also 2 number of ones, it is even, so we'll add the parity bit 1 to make it odd, and so on. In addition to that, we also have LRC, in which we will check the bit position of every Roman character. So for bit 0, we have 01011. It has 3 number of ones. It is already odd, so the parity bit is 0. For bit 1, it's 1001. It already has 2 number of ones, so we're going to add another 1 to make it odd, and so on. So what will generate is the LRC 0111010 and VRC 01100. This is our LRC and VRC codes. Some textbook may write it differently. Some may write the radio vertically, the word radio. So the LRC in that case will be located at the bottom, and VRC is located on the right. But take note, all you have to know is LRC is for the bit position and VRC is the parity bit for individual characters. Cyclic redundancy checking, CRC, this is the last one. This is the most reliable redundancy checking technique for error detection. It's a convolutional coding scheme. Approximately 99.999% of all transmission errors are detected. Most common type is CRC16, in which 16 bits are used for a block check sequence. So in this image, we can see there are D number of bits. These are the data bits to be sent. And there are R bits. These are the CRC bits. These are the generated cyclic redundancy checking bits. And it will be the entire data word, or code word rather. So we have the formula D times 2 raised to R XOR R. Let's take a look at how this is created. In the encoder, the data word has K bits. The code word has N bits. the size of the data word is augmented by adding n minus k zeros to the right-hand side of the word. The n-bit result is fed into the generator. The generator uses a divisor of size n minus k plus 1, predefined and agreed upon. The generator divides the augmented data word by the divisor modulo 2 division. The quotient of the division is discarded. The remainder r sub 2, r sub 1, and r sub 0 is appended to the data word to create the code word. The decoder receives the possibly corrupted code word. A copy of all n bits is fed to the checker, which is a replica of the generator. The remainder produced by the checker is a syndrome of n minus k. In this case, there are 3 bits, which is fed to the decision logic analyzer. The analyzer has a simple function. If the syndrome bits are all zeros, the 4 leftmost bit of the code word, again, it is just in this example, the 4 leftmost bits of the code word are accepted as the data word, interpreted as no error. Otherwise, the 4 bits are discarded because there is a detected error. Now let's take a look at how the block check sequence, or BCS, is generated. The BCS is what we will add to our data word before transmission. So in this example, we have the data word 1001, 0101, and we have the CRC of 0011, 0011. What we would like to do is we will want to translate this bits into its polynomial equivalent. So the rightmost bit is x sub 0, and then x sub 1, and to the left of it, x sub 2, and to the left is x sub 3, and so on, up until x raised to 7. So in our data word, 1001, so x raised to 7 and x raised to 4 are 1. So we have x raised to 7 and x raised to 4. And then the second part, 0101, we have x raised to 2 and x raised to 0 as 1. So we also have x raised to 2 and x raised to 0 in our polynomial equivalent. For the zeros, we will not include it since, for example, x raised to 1 times 0, it is only equal to 0. And then for our CRC, we'll do the same thing. We'll find the polynomial equivalent of 0011, 0011. It's x raised to 5 plus x raised to 4 plus x raised to 1 plus x raised to 0. Second step is we'll find the highest degree of our CRC and multiply it with our data word. Of course, we'll use the polynomial equivalent. So we have x raised to 5 times the entire data word. So we have, the result will be x raised to 12 plus x raised to 9 plus x raised to 7 plus x raised to 5. After that, we'll perform the long division by hand. So the dividend will be our data word and the divisor will be our CRC code. Sorry, the dividend will be our data word, which is multiplied by the highest degree of CRC. And of course, the divisor will be our CRC. So I'll leave this up to you. As we can see, we have the quotient, x raised to 7 plus x raised to 6 plus x raised to 5 plus x raised to 3. This isn't what we're after. What we're after is the remainder. The remainder is x raised to 4 plus x raised to 3. And it has the binary equivalent of 11000. This is our BCS. Or CRC code. This is what we will append to our data word for transmission. Error correction. Error correction includes sufficient extraneous information along with each message to enable the receiver to determine when an error has occurred and which bit is in error. Types of error correction schemes. First is retransmission, and the second is forward error correction with the use of Hamming bits. Retransmission. When a receive station requests the transmit station to resend a message or a portion of a message, then the message is received in error. Often called automatic repeat request or automatic retransmission request. This is abbreviated ARQ. This is the most reliable error correction method, although it is not necessarily the most efficient. There are two basic types, discrete and continuous. Forward error correction. Only error correction scheme that actually detects and corrects transmission errors when they are received without requiring a retransmission. This is done by using redundant bits that are added to the message before transmission. When an error is detected, the redundant bits are used to determine which bit is in error. The most popular error correction code is the Hamming code. Hamming bits, developed by Richard W. Hamming, used for correcting transmission errors in synchronous data streams. It will only correct single-bit errors. It cannot correct multiple bit errors or burst errors. The number of Hamming bits is determined by the following expression. 2 raised to n is greater than or equal to m plus n plus 1, wherein n is equal to the number of Hamming bits and m is the number of bits in each data character. And that's it.